Hello, welcome to CM Videos. My name is Dr. Michael Okereke. I'm making another video in the series of videos that I've been making on RVE modeling of different materials. And today there is an interesting material that we're looking at, and this is the idea of a curved fiber composite. I'm going to show you how to create the virtual domain, run it within ABAQUS, generate this sort of results that we see here of a tensile test, a shear test, and even go on to extract stress and strain data. And then finally, we also look at the effective properties that you can generate from the study. So that's what we're going to do in this video, and we're getting started now. So as we start now, the first thing I want to say is that this video was requested by a user on my channel, and that is Aslam Sajed, and I apologize if I didn't get that name correctly. And he basically said, thanks a lot, sir. Can you do a video on non-straight fibers? It will really be helpful. And I do think that this is really an exciting problem of trying to create a representative volume element for a unidirectional composite where the fibers are non-straight. Now, the outline that we're going to work with, as usual, is I will say a little word around the introduction to this type of curved composites, and then I'll show you how to set up this model in ABAQUS. Then we'll now go on to show the review of the simulation result that we generate from this, and then of course finally we'll extract stress and strain data. So with the way of introducing this idea of straight versus curved fiber composite, and I like to start up with the traditional unidirectional composites that are always straight. And so the fibers are nicely arranged in a linear sense like we see in the image. But however, for Aslam's problem, where he's trying to look at curved fibers, where the fibers have this kind of uneven, curved arrangement, that is a challenging thing to do. And so this is what we are going to be doing. The first question we have to think about is, how do we actually generate this curved fiber? And it's going to be generated through splines within ABAQUS. And basically, this is an image of what a curved fiber composite can look like. And one of the things that you will notice with this is, we have to define a random spline function. If you're being very deterministic about how you want to do this, then maybe your spline function can either follow a sine curve or a cosine curve or any kind of polynomial function. But in this case, we're going to allow it to be as random as possible. The other thing that is really important for us to think about is the ends of this RV, this fiber. And I've kind of decided to make the ends very straight, And so I've got a 3 micron unit length at both ends. These are like tiny tabs at the ends. The idea is that what I'm trying to achieve here is that the straight edge is to ensure the fiber faces are flat at the end of the RV. The second thing is, how do we prevent overlap of curved fibers? So if we go back to the geometry of the spline, the fiber that we want, if you look on the side view of this, so you end up seeing that this fiber configuration is circular in the way it is. So what I need to then define is a safe region around the main fiber axis. That safe region will be a region within which it will be impossible for an overlap to occur. So this is a numerical constraint that we're imposing on this model to prevent overlap. I'm going to define a region around that system. So what happens to this region is that, let's say that the radius of the fiber is r. Then there is a smaller distance of gamma that is away from this radius, which is a safe zone around which the fiber, no other fiber will enter this safe zone. And so that this safe zone becomes a region within which our fiber can take whatever configuration it wants. So it can bend, it can go up, but it must be within that region. So that means we have to find a way to define this gamma value at the time we're trying to create this model, and it will be consistent across the domain. Okay, so this could be in practice maybe related to something like the viscosity of the matrix. The viscosity of the matrix will not allow certain kind of contact between the fibers, because you need to allow for a viscosity effect so that fibers will not come in. So physically, there is a relevance to this gamma value, and we are enforcing that within this domain. So that by the time the next fiber comes in, like we're showing here, it is not able to overlap with the original fiber. And it will also have its own gamma zone and also this radial zone, like defined here. And a little bit about what we want. We want to define this minimum distance between the two centers of these fibers, so that minimum distance will define the smallest distance within which this model shouldn't see overlap. And mathematically, we can define that to say, okay, that this minimum distance must be greater than 2 times the radius plus gamma. So what is gamma? Okay, I decided to make this gamma as a function of the radius of the system. So gamma in this case is equal to some parameter, phi times r. So that again, really, it's basically a percentage of the radius will define this gamma. So in the end, you end up having a system that said, okay, the diameter, the current diameter of the fiber times 1 plus phi, where phi is this parameter, this number that I'm going to pull out to enforce this separation between the domains. And you must specify gamma for your simulation. And that's what we're going to do. Of course, I've got a code called MontCarlGen 2D, which basically creates this random positioning of the fibers. And even within MontCarlGen, there's also this feature which allows you to specify a distance within which there will be no overlap in this domain. What I mean by that is that it allows you to specify gamma. So if you just look inside MontCarlGen, there is a control deck, which is basically a text file that controls what MontCarlGen does. And there is this parameter in this control deck, which is the minimum distance. And in this case, I'm setting it at 80. So that is 80% of the current radius or the diameter of the system. So this 80% defines that phi parameter, which allows the system not to experience an overlap. So you specify this within MontCarlGen, and then you run the simulation. And when the geometry is created, then the separation, the minimum separation between two fibers must be enforced to have this minimum distance specified here. All right, the other thing that we need to do is how do we frame this fiber coordinates in the RV? Because it has to sit in space. So what is the principle behind it? If it was linear, then that's fine. You generate the point, extrude, and life is fine. Here we have a curved arrangement. So think about this fiber again in the way that I've shown it in this video, in this sketch. So there is normal length of the fiber, but what we want is that we're interested in those two ends. And the axis of the fiber is this x-axis, and the in-plane direction are the z and y axis. So there is a center for the fiber, which again, according to the geometry that we specified and the coordinate system, will take 0, y0 and z0 being the original. And then at the other end, you have another coordinate position that looks like that. But one thing that is really important that you need to bear in mind that the centers of these fibers will have to be located at y0 and z0. This is really important because you can isolate the center of the fibers, then you can create the circle, and then you can follow the sweep pattern to create the overall fiber geometry. So this is how you frame the fiber coordinate position within the RV. So you do it for one, and then you duplicate it for other fibers so that you end up having the correct representation for this curved fiber. All right, so I run MontCarlGen to the output, and this is one of the options that I get. So this is a low volume fraction constitution. So you get 6 fibers. So one thing you need to notice that MontCarlGen was used to create this end view of the RV. And this end view will be, each fiber will have a center, and that center within code is called XYO. So that means for every fiber here, you have a Y0 and a Z0 position for it, and a collection of all those is what I've called XYO here. We're going to use that later on when we start building the model. Again, if you're finding value in what I'm showing in this video, please do click the like button, or if you haven't subscribed, please do subscribe, so that contents like this will be, you'll be informed when contents like this made available. So let's jump ahead with the next step. Now the metric system that we're using will be polypropylene with the properties given here, and the fiber system will be A-glass, again with the properties given. I specified the publication of mine that I use to extract these properties. One thing you need to note here is that I've made sure that I'm modeling a low fiber volume fraction composite system with a lot of metrics in it, so 9% metrics and 10% fiber. So this will be a material that is probably most suitable for finite deforming, where you're requiring a lot of plastic deformation. So that's what we are doing with this video. Okay, what will be the loading analysis that we're going to use for here? So you got these 3 uniaxial cases. So I'm more interested in the compressive direction in case 1, just to see how these fibers will respond. Because they are kind of curved, they are more suitable, they are more susceptible to buckling and all that. So I want to see how it will react in compressive direction, especially the idea of buckling. And then we'll look at the other 2 cases in the off-axis direction because they will be dominated by the metrics. And so you see a lot of plastic deformation in the system, and it will be interesting to look at those. And then of course, like we also do, we look at the shear cases. So that's what we are going to be doing in this video, and we're going to go ahead and begin to demonstrate this in ABAQUS. Okay, here we are in ABAQUS. Of course, the first thing we need to do is, just to run you through what I've got here. So basically, I've created the model already, and I've run the simulation, I've generated the result, all completed, prior to making this video. So we're going to show those results later on, but I'm just going to walk you through the actual building up of this to make sure you understand. So let's start off with the first case and create. So what we're going to create is a fiber. So I'm going to call it fiber 1. So this is the first fiber. It's a 3D system. It's going to be created as a deformable material with a solid shape with a sweep geometry. And maybe I could make this thing just slightly bigger, 400. Okay. Now, so if we carry on with this, so clearly the first thing it says we need to sketch our sweep path, So what I'm going to do here is that I'm going to create just this first distance, the flat region, the straight edge, and I can dimension this so that I make sure that it's just a distance of 3. Okay, so that's the first one. So I'm going to make a duplicate of this. Okay, so I'm going to create and say I'm creating a copy of this same system so that it will be on the other end, and I'm starting from this start position, which is 0, 0, going to 97 and 0. So what we have here basically is a system, with those two straight edges, and then in between now we're going to have to create, the splines, but we need to create those zones that we're interested in. So a construction line to indicate the center line. So the same construction line, the boundaries of the fiber that we're modeling here is 15 micron in diameter. So the radius will be 7.5. So if we do 0 and 7.5, so that will be this point. Okay, and then we'll do 0 and again minus 7.5. So that will be another point here. So these are the boundaries that define the diameter of the fiber. So we're going to work with these two boundaries. However, we need to have a safe zone, and our safe zone is 80% of the diameter. 80% of the diameter. The diameter is 15. 80% of that is 13.75. So 13.75 plus 7.5 is around 21. So on either side, we should be having something like 21 on either side. So if we start from here to somewhere around there, so this will be 20, 0 and 21. So that will be the distance, how far, and then 0 and minus 21. So that's what we'll have also on this other side. So the two construction lines define the limit within which we are not allowed to go beyond. So this is the minimum distance that this structure will have to take in order for overlap not to happen. So once we have that sorted, then we can now come in between this region and basically try and construct our spline. So there's a function here called the splines. Again, something that is really important is in order not to allow for a sudden transition from a straight line to a curved. So I will click on that point, click somewhere next to it, and then get to the top, and then start getting close, click close by, and then go next to it, and then right click and click done. So this is important because there is a gradual movement from this straight line from this curve to the straight line, the same thing. Because if you don't do that, then you have a sudden change of orientation, which is not very physical. So this is a configuration of our spline that we're going to work with. So right click, cancel this procedure and click done. So we've got the spline, okay, that's all right. Now it says, can you construct the circle? So we're constructing our circle. We know that our circle has a diameter of 7.5. So that's the diameter of the circle. So where I click and then click done. So what we find here is that this is our first fiber, nicely created with those flat edge, making sure that we're not having a sudden transition from a flat edge to a curved edge. There's a nice flow of the data of the curve. So that's fiber 1. So I'm going to use the same and say, okay, I'm going to make a copy and call it fiber 2. So the same thing that we've used, again, it really depends on how you want to. So that's exactly the same thing that we've used before in fiber 2, but what I'm going to do with this is just to make a slight modification. So why not just flip this around to the other side? So I'm going to click on this and hold and get this mirror function. I'm going to move and my mirror line is the line through the center line, and what entity am I looking to move? That one, and click done. So it now creates the mirror image of the previous one that we have. Okay, done. So that gives us the second fiber. Okay, so we need to regenerate so that we can have, so that's the second arrangement of the fiber. So we'll do the same for the third fiber. So we'll do copy. So I'm going to get the third fiber. Okay, and now with this third fiber, so we get open to sweep and then go to the path. So we already had this previous path, so I'm going to just delete that path and then try a different case. So we start off with that, click here, close by. Okay, maybe something like this. So you close by and then you finish, you click done. So you've made all the connections for every part of the model. It looks okay. So right click, cancel, you click done. So nothing changed, so you regenerate. Okay, so you've got your shape of the fibers that look nice in this other way. So maybe you could just click the opposite of that. So if we copy that and make it number 4, so, and like we did with the previous cases, you don't have to do this. You can create unique fiber configuration. It's really left for you, but I'm just trying to use this, just to make this easy. So click on that and say, okay, I'm going to move this. This is my mirror line, and this is the system I'm trying to, and then that creates this shape, and you click done. So this is fine. And now you regenerate to also get a different shape. So we've got 4. So 6 fibers, all nicely created. So let's create a matrix block. So this is our matrix block. And we know that our matrix block, we can create it by extrusion. Our matrix block will be 0, 0, one axis, 100, 100 on this other axis. So that's the block. And then, of course, the depth of extrusion will be 100 because it's 100 by 100 by 100 micron units. So if we go to assembly here, so assembly, we select everything we've got here. Okay. So this is what I was saying. So you've got all the fibers exactly where they are, all in one place. So you now need to move them, translate them to the different positions where they need to be. So for this is okay. So how do we go about doing this? All right. So we use the translate button. But now we need to know the coordinate positions of this. So what I'm going to do is I'm going to go back to MATLAB, to my MontCarlGen. So within MontCarlGen, when you run it, it creates this domain. So this is the domain positions of the fiber that we want to locate. So what we're going to do is that we're going to walk through this domain. There is a variable called fiber coordinates data. So this is the data that, so if you double click on that, it loads it into the window. So if I clear the screen here, so the variable we're looking for is XYO. So XYO is the value that gives us the positions of this fiber. So what we're going to do with the first case is XYO 1. So this is the coordinates of the first fiber. So I'll copy that. So the first fiber, so I'll copy that. Then go back to my ABAQUS model. Now I'm going to translate this and say, select which instance you want to translate. I want the first fiber. So where are you translating it from? From the current position 0, 0 to what position? The x-axis is 0 because remember, this is the x-axis. So 0, and then space, I'll paste what I've copied across. So that moves it to this new position. So we have the fiber from there to that new position. So we'll do the same for the next one. Copy, select the instance that you want to translate, which is this. From what position, the origin, to where? So we go back to ABAQUS, to MATLAB, and find the second position. So I'll copy that link, and then basically 0, paste that, and that moves it to the second position. Okay, so we have all the 6 fibers in their location. They all look good. But clearly, if we look at what we have in MATLAB, so what we're expecting is that these ones would be replicated here, and this other one will be replicated there. So we're going to rotate it because this is the actual configuration of the system that we're working with. Okay, and this in the axis of the problem that we're working with. So this fiber here would be replicated up there. So that's very easy. So what we're going to do is that we're going to do a linear pattern, select this fiber here, okay, and we are going to ask the replication. So we remove this. So what direction are we going to work with? We're working with the y-axis replication axis, and and then let's just study and see. Okay, right. So if we then replicate that, so the distance we are looking at will be a distance of 100, okay, and that gives us the replication that we're looking at. So we've got the fiber that I replicated up there. So we need to do the same for this other one. So again, linear pattern, select this instance. So we want to replicate it again, this time around along the y-axis. So we select and go to the y-axis. And then the distance of separation will be 100 because that's what the system is, 100 micron in length. So that gives us the shape that we are working with. So we've got everything nicely in place. So again, because of the replication and the way it's been created, the volume fraction that we started off with is maintained, especially because of this replication of the system. So it's absolutely maintained. So what's the next thing that we need to then do? Still within the assembly module, because what we have here is in the assembly module. So we'll have to collect everything in one go. So I'm going to call it UD or FRP, so something like that, all of them. A fiber reinforced composite unidirectional curve. So we return all the boundaries, select everything here, click done. So what it will do is that it will merge that into one module. So if we go back to our past module, you could see we now have a UD or in exactly the way it should be, each of them in their nice cells and everything looking beautiful. So what we need to do is obviously to trim. So we'll use extrude cut here, select this plane that we want to tweak. So, and then we'll basically create this first rectangle, and then we'll create a bigger one to encompass that so that the remaining space will be extrude cut. So it cuts through the domain, and then we'll now have a really lovely representation of our structure. Okay, so this is the configuration. This is the shape that we are generating here. It's slightly different from, if whatever you do, of course, it will be probably slightly different. So if we hide this cell, so we end up with a system that looks like this. Okay, so that's the nice shape that we are working with. So we've generated the system, and we can then go ahead and use it for whatever kind of modeling that we want later on. Okay, so what is the next thing that we want to do with this domain? So we've created this domain. So just as usual, so what about material? So we create the material. So our E-glass, that's the elastic properties of the E-glass. So we stop there. What about the polypropylene? So 1.308 E9 and 0.4 is the elastic properties. So 40 megapascal and 0 is the plasticity of the keys. So what about the sections? So we now go and do a section assignment. So that's selecting just the metrics alone. I'm going to remove selected, which will be the metrics. So that leaves behind the fiber. So we double click, select all the fibers, and then we assign the properties of the fiber. And of course, we resume all and show this in sections or show this in materials. So it does show everything looks correct. So what about our mesh? So you start with the mesh. Okay, I will accept the mesh that is given to me. And then I'm going to mesh that using a tetrahedron. Okay, so the system is meshed as well. Of course, we need to apply boundary conditions and all that. And like we always do, so the first thing we're going to do with this boundary condition is create nodal sets for all the faces that we're going to use. So X face, X front. So I like to use a node option so that makes it easier for selecting the point. And we want to change this by angle. So we hover around the front edge. Okay, so that's the node for X front. So Y top. So that's for the top. So we're going to do the same for all that. Okay, so we've created all the sets for all the faces, and we can cycle through to make sure that we have it correct. So this is fine. The other thing that we need to do is if we go to the assembly module, so if we go back and switch to the assembly module, okay, these are the system that we're looking at and the materials. So there's the assembly module. So we want to find a reference point that we're going to use to apply our load. So what I usually do is I'll apply it somewhere close here, but I need to know what that point is. So I have to query that position. So I'll use the Q button. What is that point, which is here? And that is coming up here as 100, 0, 100. So I'm going to create my reference point there. So tools reference point, that place I could make it 120, 0, 100. So that's a point, that's my reference point, and still within that module, the assembly module, I could then create a set for that point. So I'm going to call it reference point set. All right, so that will be what will happen for that reference point. So our step will be a static loading step, so loading step. Of course, you could do a dynamic step, it's okay, but for this, we're just going to do a static loading step. What will be our history output? So reference point history output associated with the loading point. So what are the things that we're looking for? So RF1 and U1, for example, or maybe we just RF1, RF2, RF3, U1, U2, U3. So you specify all of that. So that will have to be associated with a certain reference point set. So we paste that. So this is what we're looking for. All these reference point values, X, Y, Z, we use all of them for our simulation. So that's fine. So that's our history value. Now with the constraints, so we have our constraint equation, because I'm going to use a constraint equation to apply the load, because this makes it easier for me to extract stress strain data later on. So this will be one position. So let's just do the first case. So let's say this is X front, because we want to do the tensile case, degree of freedom 1. And then this is -1 linked to the reference point, degree of freedom 1. So that means whatever is happening here is being translated to that face using that point. So what will be our boundary condition? So X back roller. So I'm going to fix the back in displacement, select the set for the back. So fix it in one direction. Z back roller. So we'll go the same and do the same for the back, the Z axis, and we fix it in the Z direction. And then Y base roller. So we're going to do the same for the base, and we are fixing it in the Y direction. So basically we've got this boundary condition that simulates, simulation for uniaxial case. What about our load? So we're using a displacement loading as well. So our load will be associated with a loading history, and I'm going to link it to this reference point. And in the x-axis, this will be 10 because our domain is 100. So 10% of that will be 10. Okay, so this is a situation that we can use for modeling the first case. So I'm going to rename that. So this is what we have for the tensile case, and we're ready to go. So if I create a copy of that, okay, so what I'm going to do, because the actual simulation we're trying to do is a compressive case, so I'm going to make this a compressive value, which is minus. So it's a compressive case. So it's really not a tensile case. I'm renaming that, so it has to be a compressive case. Okay, so what do we then do with the Y tension? So we copy the same model again. So this is for the Y tensile case. So I'll go to the Y tensile case. In my loading history, my load will obviously move from the x-axis to the y-axis, and it will be a positive value because it's Y tension that we are doing. So it's acting here. But it also need to move from the constraint that we're working with. So our constraint equation will no more be on x front, but actually y top, and it's 2 degrees of freedom. So basically you're loading here and it's translated to that point. That's all the change that we need to make. So we'll do it the same again. So this is what we have. So basically we've created all the models, created all the boundary conditions. Again, if you're finding value in what I'm sharing, please do click like button and do share this with people that are interested in this. If you haven't subscribed, please do subscribe to the channel so that when content like this are made, you will also be one of the people that will see it. So I've run the model. So what we're going to show now is the result. Okay, so we've got all the results set up, and we're going to run through them individually. So with the X compressive case, so this is what we find with the X compressive case. So if we analyze what's happening, so there's this compressive behavior, and like we expected, there was a buckling of the fibers due to the compressive loading. So you end up seeing the buckling of the fibers. So what happens if we review what's going on inside? So if I click on the material and show, so this is what's going on inside. So you could see how the fibers are kind of buckling and bending over due to the shear deformation. So this is the compressive behavior. So that's what we'll see, with this material. So what about the Y tensile case? So the wild tensile case obviously would be require you to move up as you push the system up as well. So what about the plastic deformation? So you could see there's a little bit of plasticity because the matrix is really shared, experiencing a lot of the finite deformation, and the fibers are kind of moving around in space. So that's what we get. So let's look at the Z tensile case. The Z tensile case obviously is similar to the Y tensile case because they are both transverse directions, and you could look at the plasticity. The plastic deformation in the model again shows that the matrix is seeing all the plasticity and everything is okay. So we could then look at the shear case, the XY shear. So the XY shear for this system, okay, so this again shows some interesting result. You end up having this face being sheared and the fiber is basically being bent around, bent. So what I'm going to do is to review what actually is going on with the fiber, because it makes sense, when you do a shear to see. So the back end is fixed, and then you see the fibers kind of returning their, the curved position as it's being sheared across. But there's a lot of shear deformation going on, within the structure, and you could see what's happening at those regions. So this is interesting result that you're getting by exploring what's happening with a system like this when it's got a curved fiber. So what about the next one, which is this YZ shear? So the YZ shear would be a similar kind of scenario. So again, plastic deformation of the matrix, the fibers in their positions, and exciting. And then let's look at the third and final case. So the same kind of scenario, so plastic deformation. So the fibers on the edges are really suffering a lot of, they're very rigid and very strong. So matrix around them is seeing a lot of deformation. And that's because of how confined the shear deformation is, because we're using a simple shear. Again, if you're interested in different kind of shear, I made a video on how to create shear deformation, for a system. And the conclusion of that video was that you really need to use a pure shear, not a simple shear. But here we're using a simple shear. So please look on the card for the video that I made on shear, on creating shear within a finite element simulation setup. I think you'll find that really useful. So those are things that we found with our result, and they all kind of make sense. They're very interesting from what we can see here. The last thing that we need to do is to extract the stress strain data, and I'm just going to demonstrate this, for one or two cases, and then we'll be done. So what do we do? So again, let's start with the X compressive case, right? So the history, create history data. So there is the history output that we requested, and because we're looking at the x-axis, so the reaction force that will be important for us will be the reaction force and the displacement, so RF1 and U1. So if we plot that, so we see the two forces. So obviously what we want to do is that we want to use Excel utility to view that data, that current data. Okay, so if we then look inside Excel, so we can copy this data that is given to us. I've already formatted a template that we are going to use. So X compression. So I've already pasted. So you paste that data in that space, and then it plots the graph for you. The dimensions, the length, width, and height of the RV are given. It works out what the Young's modulus will be. It also will work out for you what the effective strength will be. Clearly, this material is not failing because there's no damage model, so it's taking a lot of loading. So this is a virtual, it's a spurious, it's not a realistic strength. But you get what I mean. If you incorporate a damage model to this situation, then you will actually recover the right kind of strength, for this material, because this is way too high for the system that we're looking at. So we'll do the same so you can go ahead and do that. So if we go back, okay, let's try another case. So why not let's try maybe the YZ shear. Just this case, the YZ shear. So again, I'll do this history output YZ. So what will be the reaction of important? Y is the plane of loading, Z is the axis, the direction of loading. So we're looking therefore in this situation for the reaction force in the Z axis and the displacement in Z axis. So note that if it is XY, then you're looking at the Y reaction force. If it is ZX, you're looking at the X reaction force. Here, we're looking at YZ, so we're looking at the Z reaction force and Z displacement. So we plot that, and then it gives us the data that we have here. So again, Excel utility to visualize that within Excel. Okay, so that data comes off. So we can go and copy that data. Now go back to the template that I've already and look at the YZ, which is this. So we can paste it into that environment, and then again it works out the Young's modulus, works out the effective strength and all the plot. So the final thing is that I put all these cases together in this stress strain plot for this material. So you could see the compressive case, the Z compressive case. Again, I reduced the strain level so that we can just see the linear elastic limit section, which is kind of most representative. So you can also see the X tension and the Y tension, the Z tension and the Y tension, and all the shear cases. And if you zoom in more closely, you could even see nicely what's happening here. So in the transverse direction, X and Y transverse direction, there's not much difference between the two. So this is okay. In the shear, there's a lot of issues, there's a lot of values, stress build up in the XY plane because you're shearing on the plane of the fiber, so you're moving it around. So the fiber is contributing significantly. On the other planes, it's not really contributing as much. There's kind of, again, not much difference between the two. So if you then go back finally and look at the values that we have here, so you could see what's happening, the compressive case, the modulus, this is the fiber direction, the modulus is a lot. This, again, is a little bit less than what you would get if they were linear oriented values. So if you make a calculation on this kind of thing based on, let's say, linear arrangement of fibers, this number will probably be somewhere around 10, 12 using rule of mixture. So clearly the fiber orientation, the ondular, the curved nature of the fiber is affecting the result across board. Okay, so but this is the information, this kind of thing we want to find out here. And then you look at the values of the strengths associated with the system. So that's really what this video is all about. So I've shown you how to do this, for a curved fiber situation, but some of you may be interested in actually doing this for a straight fiber. So there's a video that is here which shows you how to do this within a straight fiber. If you're interested again in how to extract, stress and strain data in the way that I've used here, again, there is a video that is here that shows you how you can do that. So thank you for your interest in this video, and I'll see you in the next video. Bye-bye.